focus is on resource efficient and cleaner production in the chemical industry, with a dedicated focus on volatile organic compounds. This is a narrow area. This is one aspect of chemicals production, but it's reaching quite far actually, because VOCs are used in many industries. We will discuss a few examples from cleaning in metal manufacturing, as well as spray painting, which is an application of VOCs, but also applications in printing, in offset printing, starting from the inks themselves to cleaning. All this is VOCs, volatile organic compounds. Let's start first with the focus on RECP, just to memorize this again in a nutshell. What are we talking about? What are we focusing on? What are we maybe not so much focusing on? The focus of RECP, as Sergei has mentioned in his introduction, is on prevention. What we want to talk about in the first place is to use our common sense, to use our understanding of processes in order to improve them, to increase their efficiency, to increase the useful application of materials, and to minimize the generation of waste and of environmental impact. In most cases, this creates benefit for the environment, because if we reduce waste, if we reduce emissions, if we reduce wastewater, this is good for the environment, obviously. But at the same time, we are doing something good for our pocket as an entrepreneur, because all the material which we do not waste, we do not have to buy in the first place. So in our hierarchy, prevention ranks first. We try to mitigate any wasteful use of materials, of energy in the first place, and only waste emissions we cannot avoid completely. We try to recycle, to reduce, and only the minimum then, where we are not inventive enough or creative enough or knowledgeable enough to avoid it, this we have to landfill, to treat, to incinerate, whatever then a proper solution might be. So our focus is on prevention, to use our imagination, to use our knowledge, our creativity, to find as many opportunities as possible to properly use the materials which we have in our companies. This chart here shows the practical approach, because the vision of RECP is a quite broad one. It ends up somewhere with zero emissions, a zero carbon industry. We start small. In the first place, we look at what can we do by good housekeeping, by doing things in the right way, by training people properly, by providing proper set points, proper concentrations, so that we can maximize the benefit with a minimum of effort. That's a rational approach, isn't it? To make best possible use of what we have, not to waste anything intentionally. Second step in this approach then is the application of appropriate technology, wherever necessary, over time, to upgrade our technology so that it's more efficient, better, more energy efficient, less wasteful. This can mean also better process controls. This not necessarily means completely new equipment. This can mean the addition of sensors, of probes, so that we have better control of a process. And then, as a natural extension of the concept, we use synergies in between companies by applying what is called industrial symbiosis. So that waste of some company maybe can be a useful raw material for another company. That waste heat from one company can serve as district heat in a region or for other companies. And the final goal then is by innovative thinking to identify new products, services maybe, which can provide all the benefit we want out of using materials, out of using energy in a way that per design, out of the design of the system, waste minimization, environmental impact is minimized. But to come back to my starting point, we start small. We start with what we have, trying to use it the best possible way. Now, for this afternoon, we are basically talking about volatile organic compounds, which basically means solvents, which basically means hydrocarbons, which are used in a magnitude in many, many applications all through our industries. We will talk about what are solvents actually, what are their properties, what makes them so special in handling them, where are we using solvents, in which industries, in which processes, what are the hazards, what makes the solvents so special, how to control them, which protection to use, also how to communicate the associated hazards. And then we will dig into 3 specific applications, which I'm sure all of us know, which basically is cleaning of metal surfaces, which basically is painting and coating, and which is printing, because these are actually the processes where most of the volatile organic components in our industries are used. And we will explore a little bit what potential there is to reduce the consumption and to increase the efficiency of use of VOCs, because still a lot can be done. Still, we are not exploring the full potential of prevention as we were starting with. So, but let's dig into things. What are solvents? As the term says, solvents are there to dissolve something. They are not reactants. They have no specific function apart from solving something. Dissolving oils, grease, paints, maybe inks, maybe pesticides, so broad range of application. They are also used quite frequently in cleaning. They include ubiquitous substances like gasoline. Gasoline is a VOC. Acetone, which we use for cleaning, maybe in the laboratory. Alcohol, which we use for a multitude of purposes. All these spirits, xylene in paints, methylene chloride, trichloroethylene, perchloroethylene, all these chemicals are VOCs. And the main property of these VOCs is that they evaporate very easily, that their vapor pressure is quite high. By definition, a VOC is something organic material which evaporates at standard pressure at lower than 200 degrees. So it's basically all the organic liquids which we use. In this slide, to make a very long story short, we have the most frequent applications of VOCs in our industries. And from this we can tell basically they are everywhere. In spray painting, as constituents of the paint, we have solvents like toluene, xylene, spirit. In cleaning metals, we use a lot. In cleaning tools, in cleaning equipment, we use acetone, methyl ethyl ketone, toluene, mineral spirit. In production of epoxies of fiberglass, which is an important area in reinforced plastics, which we use for construction, we use acetone. In the printing processes, we use isopropyl alcohol a lot as a dampening agent. In screen printing, in dry cleaning, in electronics, we use a lot of these solvents. Now, one important property, not for all of these VOCs, but for quite a lot of them, is a danger which comes out of their flammability, which is characterized by the flash point, which is the point, the temperature point above which a liquid will render gases which can be easily combusted, incinerated, ignited. If the flash point is below 21 degrees, we call it flammable. This is something which is very ready to combustion. If the flash point is between 21 and 55 degrees, we call it incinerable. It's more difficult to ignite, but still it will very readily burn. Why am I mentioning this? These are flash points of some liquids we probably deal with every day. I just made a short list of quite a few, which are basically everywhere. Petrol, which we use in the car unless we use diesel, has a flash point of minus 22 degrees. So basically it will form vapor which can be incinerated right away, mostly everywhere. Diesel is higher, 55 degrees. That's why in some regions of this planet they have to heat the diesel tanks in winter. Isopropanol, which is used in printing a lot, has a flash point of 12 degrees. So whenever we have isopropanol in bigger quantities, whenever we have spillages, we need to be careful. Acetone, minus 18 degrees. Vodka at 28 degrees. So watch out. Beer is more on the safe side. Regular beer at 5% alcohol has a flash point of 81 degrees. So it's not very probable to ignite. Next to the flash point, it's important to discuss the limits of flammability, because we remember well from our education that there is an upper range and a lower range of flammability. Like when discussing a boiler, it's a question, it's a matter of the right mixture of air to fuel. If the atmosphere is too rich in air, the fuel is too diluted. If the fuel is too concentrated, there is not enough of oxygen for incineration. So, using the example of a car, gasoline is very flammable, but a full tank without air will not burn. if the tank is really full to the top, if no air is present, I can do welding in theory on the tank. It's all a matter of the right concentration. This is these limits, this lower and upper flammability limit, the example of acetone. Below 2.5% acetone in ambient air will not burn because simply there is not enough energy in the mixture. And above about 13% acetone again will not burn. In between 3 and 13% acetone will burn readily, very nicely, very nice fuel. So when doing an analysis of hazards and when trying to find remedies against hazards, this is important to know. What is the upper and the lower limit of flammability? Because in any case, by the measures we take, we need to stay outside this range, either below or above, but not in between these limits. What this guy is very daring. This is a roadside workshop in Mexico, and this guy is repairing the fuel tank. I'm sure he's believing, because if we think about what we've just discussed, as soon as there is a mixture of air and fuel vapor, this is highly incinerable. And what this guy is doing is he's working on a fuel tank where he for sure is not knowing whether it's completely empty. Completely empty means dry, no fuel at all, or whether it's really full, so that in any case he stays out within the range. But in confined spaces, in a tank, in a container, in a can, we quite quickly can be within the combustibility range. So what are the immediate lessons learned before we discuss about health risks, because before we discuss about other hazards? Whenever we use organic solvents, volatile organic compounds, maybe in these applications which we have discussed earlier, because we are a paint shop, because we are cleaning, because we are a print shop, we must make sure that there are no open flames, no sparks, no faulty electricity, no contacts, nothing that can draw a spark. Containers which we use should be constructed to hold flammable liquids. That means enough space, that means a lid which will close, that means a funnel to guide the liquid where we need it. The containers need to be ground so that there cannot be static electricity, so that it's impossible to have electric sparks. This is relevant for many solvents which we use in cleaning. This affects gasoline, this affects methyl ethyl ketone, which we might use in inkjet printers, for labeling, even food maybe. Acetone, which we might use for cleaning, toluene, xylene, which might be constituents of paints. So this applies to quite a wide range of organic liquids. And we need to make sure, what we will discuss soon, that these are the ignition sources and the solvents are thoroughly separated. There is a publication which I want to draw your attention to. It's in the next slide, which deals with best practices regarding safe practices when using solvents. And this includes a lot of small details regarding how to store, how to transport organic solvents. I put here in this slide just a few examples, maybe the most important things to think about when handling bigger quantities. And bigger quantities means more than 10, 15 liters of organic solvents. We have it as a law that there need to be a gas displacement line whenever I'm moving around more than 5,000 liters of solvent. That means that the gases from filling a tank, the gases which accumulate in the tank, which will be displaced by the liquid, need to be taken back to the tanker so that there is a closed system where no gases can escape from gasoline, from all the other solvents. We need these gas displacement lines. We need to make sure about proper storage. Proper storage means original containers which are strong enough that they can drop from a truck, which are stored in a closed compartment, if possible away from areas where people work, out of the sun, in the shade, so that heat does not cause additional vapor pressure, additional escape of fumes. When handling, when pumping organic liquids, a few suggestions are canned motor pumps, so that the motor cannot spark. Flange seals, so maybe around the flanges, additional covers, so that when leakages happen, they cannot drip to the ground, form little bones of organic solvents. Hermetic valves I will show in a minute, and on bigger tanks, floating roofs, so that there is no gas phase which can go to the atmosphere. This is this publication, European Sealing Com. This was out of the VOC regulation, which was published in 2002 or 2005. They did a thorough analysis how organic solvents escape to the atmosphere. And from a survey of European chemical industries, it was found out that actually 2/3 of organic solvents escape to the atmosphere from valves, because the stuffings leak or the flanges leak. So for all these solvents, there are specifically dedicated hermetic valves which have a double jacket which minimizes or completely seals leakages to the outside, because this is the biggest problem. Then come basically relief valves, safety relief valves, which when faulty also discharge vapors of organic liquids.
Yes.
Next thing I wanted to draw your attention to is relief valves, safety relief valves, because this I have seen myself, that if a safety relief valve deploys, it will never seal again, and if it's not exchanged on the spot, it's a constant hazard. And then comes tanks, tank ventilation we discussed, floating roof tanks or these closed circles to contain gases. And only then comes pumps and flanges. And for pumps we have solutions. We have these canned motors so that the spark in the motor is completely separated from the hazardous liquid. Now comes the second big problem, which is probably the major problem, I agree, which is attached to solvents. Just in general, before discussing in detail which solvents have which properties, most solvents, or almost all solvents, are at least irritating to eyes, noses, throat, to the skin in general. This can be a desired impact, but usually it's not. Solvent make you dizzy, even high. You will feel weak, sleepy. They definitely will affect your judgment or coordination. This we observe even nowadays, sometimes in painting. For example, when people get used to the solvents, do not use the personal safety equipment properly. So definitely these materials can affect the judgment of people who work with these materials continuously. It will cause internal damage and irritate the skin. Most solvents can be absorbed through the skin and then cause internal defects. What to be prepared of, and this links then to personal safety equipment. And it would be interesting to discuss what reflects in law here in Belarus. Direct splash into the eye definitely is a danger, can irritate, requires eye washing flasks in the immediate area. Solvent vapors will be irritating, especially if you're using contact lenses, for example. So in a lab, you cannot use contact lenses because the solvent will condense in the small gap between the lens and the eye, and the condensate of the solvent will cause damage to your eye. So when dealing with solvents, it's highly recommended to use goggles at all times. The most common route of exposure is inhalation. That links then also to personal health and safety equipment. Some solvents, but unfortunately not all of the solvents, have a very strong smell, and this alarms people. But this is not true for all the solvents. Some solvents, even like benzene or so, you will not recognize quite readily. All these health risks translate into numbers, which come from experiments with our relatives regarding permissible exposure limits. And these, for most of the solvents we are talking about, are quite strict. So I agree, if we reliably stay outside these permissible exposure limits, also risk of fire, risk of explosion is very low, because we're talking like for trichloroethylene, which is really nasty. We're talking about 50 ppm, parts per million. For toluene xylane, which is contained in many paints, we're talking about 100 ppm, which are really low numbers actually. And as soon as we are using these solvents, or whether it's a print shop or these inkjet printers, which we maybe use to mark things, to put a base before date, or to put a charge batch identification number, is 200 ppm. So these are really low numbers, and in the areas where we use these substances, there should not be any spills or little puddles of liquid and so on, and there should be proper ventilation. The direct dangers associated with some common solvents are listed in this slide. Benzene, you mentioned it, is really bad, causing leukemia in the end. Hexane, which is constituent of gasoline basically, is causing neuropathy, so causes your nerves to deteriorate. Methanol, we know from the news, we know maybe from our grandparents' experience in distilling at home, can even cause blindness. This is very bad for your vision. Carbon tetrachloride, which was used until not so many years ago for cleaning, for dry cleaning even, is very bad for liver and kidneys. Certain freons, which are also banned now, interfere with your heartbeat, and also some glycol ethers, which are used in electronic industries, are really bad for fertility and young life. So, what are activities which expose us to these chemicals? Because from understanding the hazards actually in the workspace, these chemicals should not be present. Under which conditions can we be exposed to vapors of these solvents? Probable source of solvent vapors with the properties which we just discussed is spraying and spray painting, because still in many applications we use solvent-based paints which contain xylane, toluene, all these solvents. Sometimes maintenance is a major source of solvents. When people still use solvents on rags to clean bearings, to clean delicate parts of machines. Cleaning of parts in metal processing, cleaning before painting, cleaning before galvanizing can be a relevant emission source. Okay. And then we are talking about larger spills, releases from faulty containers, from spills, from flanges. Some exposures. Mostly it's nowadays by spraying, by evaporation from bigger tanks and from spills. Now, what can we do to minimize exposure? We have three strategies here. First strategy is straightforward. Wherever possible, let's eliminate. This is prevention. This is a common sense approach. But there are limits to this approach. Not in all applications I can simply do with the solvent. There are some areas of application where it's still needed, but this should be our priority wherever possible. Let's eliminate solvents, organic solvents, VOCs. This comes from experiments. And we will see later on in the examples that quite some progress has been made in this respect. We can do with solvents, with organic solvents, in many applications. Second strategy, if first strategy, elimination, is not applicable, is substitution. Also straightforward. If it's for sure a good choice, if I can replace a very problematic solvent by a less problematic one. We will see a few examples later on also where this is applicable, and especially in cleaning, even in cleaning very delicate parts, where there is common notion that we still need solvents for cleaning. We cannot do it water-based or else. Still, there are less problematic solvents than trichloroethylene or perchloroethylene, just to name these two. And third strategy then is an extrapolation of the second one, substitute a solvent with a less volatile solvent so that vapor pressure is lower, so that exposure is less, that there is less solvent evaporating. So definitely elimination is appropriate strategy, and it's applicable in many cases, else substitution. How can we reduce the exposure to chemicals? To enclose a process might be a strategy, to confine it to some space, to have a painting booth where solvents are used and only there they are used. To have a dedicated cleaning area, not using solvent all over the place, all over the factory, but only in dedicated areas. Second suggestion, which is also common sense, but very rarely applied. Whenever we use solvents, let's cover the tanks, containers which contain solvents. And this starts from small paint jobs where I use a little solvent to clean my brush. Let's put a cover. Whenever I use solvent in a little jar to clean a needle of a spray gun, let's put a cover so that all these containers where I keep some solvent when cleaning a printing machine, let's cover it at least before and after use. Whenever there are solvents, there should be ventilation. We will discuss in a minute different types of ventilation. General ventilation or dedicated exhausting of vapors from a dedicated area. Solvent should always be combined with ventilation. And the last one is linked to the last one. Whenever we use solvents, there also should be general ventilation so that there is in any case a dilution of any vapors which might form. General ventilation can be just a roof fan supplying fresh air to the area at a renewal rate of 2-3 times per hour so that we have good basic ventilation. Now, ventilation ideally is locally wherever we use solvents, like here in this degreasing tank, they're directly should be an exhaust. Ideally also the exhaust should be combined with the air supply so that there is a balance of air and the vapors cannot escape to the sides, but it's like an air knife taking any solvent gases directly away from the operator who is working close and from any potential sources of ignition. But of course the main person who has to be protected is the operator. In case this exhaust ventilation is not effective enough to guarantee our maximum permissible levels, we have to talk about respirators. And respirators are almost a standard in industrial paint shops, for example, because else we cannot avoid the exposure to solvents unless we change the material. We move away from solvent-based paints. Some examples we'll discuss in a minute. So in case this local ventilation is not good enough, we need respirators, and respirators do not mean dust masks. A dust mask does not protect against solvents. It's good against general dust, maybe good against grinding dust and so on, but not against solvents or hazardous chemicals. There are limitations, of course. If we look at this guy with his self-sustaining respirator, this guy probably is not comfortable. He's probably very hot. He's sweating. He cannot spot a beard. So there are many practical restrictions why people do not like respirators. But solvents in higher concentrations go together with respirators. There is no way around. Additionally to what we have seen in the last slide, we have of course different types. These small respirators with the filters which can be changed, a full visor to protect the eyes also, self-sustaining with filters and the fan to support the breathing action, or even linked to a compressor in case, for example, you go for tank cleaning or so, where you need to have your own air. All different types, definitely not this type. So to make sure that when we're using solvents, that we use the right mask and the right filter is really important. Also, these filters have a date of expiry, so they should be regularly checked and renewed if necessary. The cartridges might be or will be dedicated for some solvents, so we need to make sure also that we are using the right cartridges. Yeah, to make a long story short, respirators we need to exercise with, even if we don't like to do that because we are sweating, it's time consuming. We need to do that, and with most respirators, this is also something I have some personal experience with. It's difficult to explain to people that we cannot wear nice beard together with a mask. So training is important. Okay, Equally important for protecting the skin, because most solvents will penetrate the skin and then cause damage to the tissue or to the internal organs, is the proper gloves. And proper gloves with solvents, with chemicals, means not regular working gloves and means not latex gloves, but proper PVC gloves, which actually block the solvent from entering the skin. The thicker the glove, the better. Of course, the thicker gloves are hotter, are not so comfortable, but whenever we do decreasing operations like these, where we count out parts, check parts, proper gloves should be worn. Yeah, there are different classes of gloves depending on the chemicals we're using and depending on the time of exposure. Now, all this what we are discussing now, all these hazards to human beings, to the operators, all these risks, fire, explosion and so on, where do people get relevant information from? Nothing new. Material safety data sheets is the instrument we are talking about. And still, after so many years, this is not an instrument everybody is readily using. This really should be a habit that as soon as we are using chemicals, we should have up-to-date, comprehensive material safety data sheet in the house and close to the workplace where we're actually using the chemicals, because that is where we need all this information. And I agree, we will discuss this in a minute, looking into a full material safety data sheet. The information is very comprehensive, quite lengthy. Some material safety data sheets nowadays have 40, 50, 60 pages. But in this case, a knowledgeable person should extract the relevant information and translate it in a way that the operators can use the information and that the information can be used in training regularly. What is the information now which is included in a material safety data sheet? First, it's the formulation, the chemical. And this is something, at least according to the European law, regarding hazardous constituents. No trade secrets apply. So whenever something toxic, cancerogenous, really hazardous is used in preparing a chemical, it has to be declared. And we really should make sure that we get good telling material safety data sheets with all the chemicals which we buy. We have a small suggestion in this respect. This comes from Environmental Management Systems, from ISO 14000. We make it a small paragraph in purchasing conditions that the delivery of a chemical is considered complete only with the material safety data sheet, which in plain language means we will pay for the chemical only if we get also a material safety data sheet. Quite straightforward, and usually, to my experience, this works. Then we get also the recent versions and complete versions. We have the formulation, we have the hazardous ingredients, we have physical data, and then we have all the information which we need. What hazards are associated with the chemicals? What precautions should I take? What shall I do in case an accident happens? All these first aid measures. Measures in case of a fire. All this is included in the material safety data sheet. And all these I can take and prepare in a telling way for the operators, maybe using pictograms, showing the personal safety protection people should use when dealing with the chemicals. Maybe in assigning proper space for storage, deciding on storage conditions for the chemicals. The information how I should manage the chemicals will be in the material safety data sheets. This material safety data sheet here is for a material which is used a lot in print jobs, in offset printing, in the tamponing solutions, for preparing the clichés. We use a lot of isopropyl alcohol. Now, it's flammable and it's a hazard to health. I should not inhale it. It will make me dizzy. It will make me sleepy. I have to know that, and people working there have to know that. And the storage of these should be done accordingly. Only what I need for a day should be at the machine. The rest of the isopropyl alcohol should be stored in a confined area, well outside the workspace and so on. P phrases, the precautionary phrases, tells me what to do in case of fire, what to do in case of contact, what to do if something hits my eye. Tells me rinse continuously with water for several minutes. What does that mean in a print shop? There needs to be a source of water close by so that the operator who maybe gets some droplets of isopropyl alcohol in his eye actually can rinse his eyes and so on. Store locked up, so bigger quantities like 1 cubic meter box pallets should go in a designated confined area, should not be allocated close to the actual printing machine, and so on and so on. All this information is there. Precondition is I have this in my factory and I have a person who deals with these material safety data sheets. Now, general information on the chemical we have. What comes next? As a general rule, all the containers containing chemicals need to be labeled, if possible, labeled by the supplier completely. But also all the containers I might be using inside the company to move internally, to supply a machine with a chemical, also all these should be labeled in order to avoid accidental mixing, spilling, mistaking chemicals. Also, all the containers which I use internally should be labeled. They should show what is the product, who has supplied it, because this is the source of information in case something goes wrong. If applies, what hazards are associated with the chemicals, and what are the hazardous ingredients. This information should be contained on all solvent containers. And a small piece of advice, let's not use food containers for solvents. Never. Because this still is a relevant, you wouldn't believe it probably, but this still is a relevant source of accidents, even in Austria, even in Germany. That people take small quantities of solvent to the workplace just for a little bit cleaning or just in case I need this for some repair or so. And then after 2 months, nobody knows anymore. It's a hot summer day and somebody takes this by accident, and to swallow a gulp of white liquid is already a serious accident. So all the containers we use, also the ones we use internally, should be labeled. I will show a brief model for such a label, which you can keep on site for such cases, but all containers should be labeled. Product identifier, supplier, chemical, if hazards are involved, if possible pictograms, because you grasp the pictograms much faster than any wording or right. Applicable signal words, hazard statements, and precautionary information. This takes us to pictograms. These are the pictograms which the global harmonized system suggests. This is built on the UN, United Nations system. This was sort of adopted also by the European Community. These symbols, these labels are self-explanatory, aren't they? This stands for explosive, incinerable, oxidizing. Yeah. This is a gas, compressed gas. This is dangerous for the environment, the dead fish. This is general hazard. This is bad. So, yes, yeah. This is, what's the English word?
Acid.
Acid and caustic, which is bad for the skin, and this is toxic. According to the harmonized system, the labeling should include also hazard statements, these H phrases, I will show a few examples in a minute, and precautionary statements. Signal words indicating what precautions to take. You will remember this from your experience looking at material safety data sheets or looking at labels for chemicals. These are just some examples. This is about 200, 250 numbers identifying if an H is leading the number, identifying hazard statements, like the flammable gas, like acetylene or so, would carry a H220. A flammable gas like CNG or something would be 221. If something causes cancer, like some cyanides or some chromium salts, it would be H350 and so on. Phrases with a P initially are precautionary statements. This is the advice what to do in case. P103 is a quite generic one that indicates that in any case people working with this need to have some basic information. Read label before you use the chemical. This applies to lots of chemicals actually. P102 is keep out of reach of children. This also applies to many chemicals. This is maybe something to apply to ourselves at home. How many cleaning agents and so on actually should be stored away from children. Again, also here there are some 200 such phrases. Now, when a truck delivers some chemicals, the the truck should carry actually an orange plate with two numbers. The upper number indicating the hazard which is associated with the chemical, and the lower number which identifies clearly the substance which the truck is carrying. So basically this can look like this. Upper number 33 means highly flammable, because this truck is carrying gasoline. 1203 is gasoline. And what is the purpose of this? The purpose of this labeling, of course, is that the fire brigade knows what to do in case there is an accident, in case there is a spill, in case there is an incident with this. This truck broke down. Now the firemen have to take out all the contents. If there is no proper labeling, how should they know what to expect when they start unloading the truck? If this was not there, how should they know what the truck is carrying? And it's not fair to the fire brigade to call them for something where something explosive, something flammable might be carried, and where they themselves might run a very high risk then when trying to protect others. A page for the ones who are interested, who maybe like some reading in analyzing old accidents and so on. I can highly recommend this page. It's from the National Bureau of Transport of the United States, and they have a collection of accidents reports where they put what happened and why has it happened and what could have been done to prevent the accident. And this is really very instructive to read through this for general information, to create awareness, but also when you're preparing a risk analysis for an industry, being it your own enterprise or for another one. You wouldn't imagine what accidents have happened, although nobody thought they could happen, and what chains of events can develop where nobody thinks about this in advance. If I take your signal correctly,
yes,
it's time for a break, 15 minutes, and then we continue. A second part will be more examples of a few industries, how to apply our strategies of eliminating risks and substitute solvents. If possible, let's eliminate organic solvents. That was the conclusion out of the first block. How can we eliminate? Where can we eliminate? A few examples here. In dry cleaning, clothes, for example. In the old days, trichloroethylene, perchloroethylene were used. If we still use these, instead of using water-based cleaning, closed-circuit machines are a must, in which these solvents are distilled. The dirt grease is extracted, is disposed of, and the solvent is completely recycled. These systems have no emissions, and they work in Europe. It's compulsory for every dry cleaning installation to use closed-circuit machines. In degreasing of metals, very likely, and we will see an example, we can use degreasers with an integrated circulation system, or in some cases water-based systems, or sometimes different systems like CO2 pellets for degreasing, but this is not so widely accepted. And domestic solvents have been replaced, at least in Europe. I cannot buy them anymore, not in any shop, not in any pharmaceuticals. Non-industrial paint use is mostly low solvents, high solid paints or water-based paints. We'll show you an example in a minute. And in industry, much solvent painting has been replaced either by water-based painting. We will discuss the drawbacks also in a minute, because there are some, or by power paint, by applying powder in a fine form, by curing it then at a temperature of 160 to 230 degrees without any solvent. In chemical processes, there is some substitution in between solvents, in glues, adhesives as well. In printing, there is a shift towards water-based ink, but there is a lot good housekeeping measures, which we will also discuss in a minute. And especially in printing, there is a lot of end-of-pipe technology that we extract the vapors, and we have a post-combustion plant where the solvent-loaded air is incinerated. In wood preservation, closed technologies are used. In the chemical industry, a lot of inspection, a lot of maintenance was the answer to reduce emissions of solvents. And in fuel storage, which accounted also for a big part of volatile organic carbon emissions, internal floating roof tanks have become a standard, minimizing the venting of organic gases into the atmosphere. Let's start with cleaning, because cleaning of metal parts from grease, from oil, is still a widespread application of organic solvents. The next 3-4 slides show substitution routes. This is a description of the past. All this actually mostly has happened. So the carbon tetrachloride, which was used until 1940s, 1950s, in the first step was replaced by trichloroethane, trichloroethylene, then by perchloroethylene, and the perchloroethylene is also now constantly being replaced. We will see in a minute. So these stages of substitution have happened actually through the industry. Hydrocarbons from crude solvent mixtures, which included aromatic compounds, we have moved completely to mixtures without aromatic compounds. Only alkanes are used. And another route of substitution, which is then linked to our examples also, is the use of alcohols, especially esters, ethers, to substitute alkanic solvents. A major route of development was the use of caustic soda in combination with effective detergents, and the further development of biodegradable and less toxic constituents in complex mixtures for degreasing, which is actually the standard. at the moment. And these are parallel development lines which are at present going on, that the chlorinated solvents, which we saw in the first slides, and the hydrocarbons, which we saw in the second slide, are being at least partly replaced with carbon dioxide, supercritical carbon dioxide, or carbon dioxide pellets, completely changing production processes. The keyword here is dry cutting, dry machining, which works for certain applications, but especially in this area here, with aluminum, with cast iron, we have very good experiences with dry machining. So getting away with all the oil and grease from the metal manufacturing, which requires degreasing and dry machining, so that there is no need for cleaning anymore. And this is the future, maybe laser degreasing, nano cleaning with specific constituents. 3 development lines, the large operators producing big quantities of specific parts, mostly have switched to automatic and closed installations using different chemicals, chlorinated ones, non-chlorinated ones, using esters also. The small ones have problems. They depend on the suppliers of cleaning chemicals, like Dow, for example. For them, especially for them, specifically for them, this chemical leasing is a very appropriate strategy, where the supplier, the former supplier of the chemical, comes in and takes over the whole cleaning operation, and the company, which does not have an interest in understanding all the details of their cleaning operation, sort of outsource the whole process and pay, for example, per cleaned part. They do not buy the solvents or the detergents anymore, but they pay the supplier, like Dow, like others who offer that, per cleaned part, per square meter surface they clean, and like these completely outsource the problem. What we notice is that wherever we go on this planet, the regulatory framework becomes tighter, and there is more and more pressure either to go into the direction of completely closing systems or outsourcing operations. Now a few examples. A manufacturer of heat exchangers, like for radiators for engine coolers, these aluminum lamella heat exchangers, which we also use in air conditioning. They started with trichloroethylene, and they had some legal pressure to stop this. They did lots of experiments. However, they have a serious problem. They have very narrow gaps, 0.6 millimeters and less. So whenever they use water for cleaning, because of the capillary effects, it takes forever to dry the water out of their heat exchangers. The strategy which they followed was not to use trichloroethylene anymore, but perchloroethylene, and in a completely closed cycle. So they are using now a integrated steam degreaser, where the steam then is collected, is distilled, only the oil is discharged as a hazardous waste, and the degreaser works in a closed cycle. Example number 2, I will explain in a minute. Example number 2 is related to spray can cleaning. So in a company where they do lots of small repairs at the end of the line, they use a lot of spray cans with paint, with enamel, and they have to be cleaned also. The tips of these spray cans have to be cleaned. They used to do that with solvent. Now, this is example number 1. You recognize these heat exchangers like for air conditioning units. These are aluminum lamella, very thin lamella, and there are copper tubes running through this lamella, and this is soldered together. And in order to have a good quality of the soldering, the parts where the aluminum meets the copper need to be absolutely clean. There cannot be any oil, any grease, or any water. And these gaps are very, very small, just 0.5, 0.6 millimeters. So in tests, they found aqueous cleaning, water-based cleaning impossible, because of the capillary effect, the water would be too difficult to dry off. So they continue to use perchloroethylene, but in a completely closed cycle. So we have a conveyor here where the heat exchangers run through the machine. In baskets, they are entered into the vapor of perchloroethylene. The vapor washes all the oil and grease, which is from stamping and cutting and so on the lamella and on the pipes. And then the vapor is condensed, distilled again to separate the oil and the grease, and the perchloroethylene is reused. Perchloroethylene consumption is minimum because this cycle is very tight. Second example, these are the tips of the spray cans. And initially, they were cleaned just with thinner solvent, put in little cups, the tips plus the solvent, and then overnight, the solvent would dissolve all the dried paint, and the tips could be reused again. Problem was, as nobody covered these cups, pretty much of this solvent actually evaporated. So the strategies which they found worked were first, after spraying, to use a cloth and wipe off most of the residual paint. So most of the job actually was done like this. Then to tilt the can and spray the nozzle clean. Only then for tips which could not be cleaned like this, they applied some solvent, and additionally to all nozzles they applied some lubricant like this MOS2 as a separation agent. And this strategy then in the end reduced their solvent consumption by more than 80%. So this worked quite nicely. It's of course a little bit more manual effort to clean the spray tips, but it reduces solvent use significantly. This is a third example of a company we have been working with over the years. This Ventrex is producing valves for tires, so air valves for tires. But it's also producing compressors, small compressors like you use in more expensive cars instead of a spare wheel. And similar parts. They also produce compressors for air springs in seats, in trucks, and such sophisticated parts. What we see here is the turning of some parts for their air valves. Basically, these are very small parts, not bigger than maybe 10 to 20 millimeters. The hole of the drill is sometimes less than a millimeter. So the problem is that the cutting lubricant which is used, because they cannot do dry cutting, so far they have not been successful. So the cutting lubricant sticks into these small holes, tiny holes. So the degreasing is quite an effort. What they did was, until a couple of years ago, they used a perchloroethylene closed cycle, like I described earlier, for this Luvata, for these heat exchangers. They used the same system, closed cycle, conveyor, baskets with the parts, steam degreasing and distillation of the perchloroethylene. Then they switched to a modified alcohol to get rid of the chlorinated solvent, and this worked very nicely. Dow provides a whole palette of some 20 almost specifically designed alkoxypropanols for this purpose of degreasing. And they have been using these now for the last almost 10 years. And their hazardous waste cost has come completely down because there is no waste of perchloroethylene. They are now just discharging off a little bit grease and oil, which they extract from their parts. But almost no hazardous waste anymore. So there are some applications where you can completely get rid of chlorinated hydrocarbons with these alkoxypropanols, which come more or less at the same price like the chlorinated solvents. There are few other ideas how to reduce solvents. One small example from a supplier to parts for companies supplying aero parts going to airplanes. They used to clean with cotton rags and solvent, and they switched over to these SAT wipes. This is a company supplying very thin cloth, which is microfiber, which is impregnated with a specific solvent, but very little solvent. This works very nicely and reduced the quantity of waste by more than 80%. So these pre-saturated wipes are also a suggestion, and something that should always go together with rags, solvents, and so on is containers with closed lids, so that no solvent can evaporate to the atmosphere. An alternative, especially for slightly bigger parts, which have bigger holes and are easier to clean, is water-based cleaning. In water-based cleaning, usually we have a tank with a mixture of caustic soda, some detergents, and then rinsing. And the two problems which sometimes make it impossible to use water-based cleanings are the bigger space requirements, because we need this degreasing tank and then a rinsing cascade, and requirements to dry the parts afterwards, because the last stage usually is drying the parts, which requires some energy but also time. So the main problem with water-based cleaning is mostly time, process time, because instead of one degreasing tank, we now have about 4 tanks plus 1 dryer. So in a fully automatic plant where lots of simple parts are processed, this is possible, but with smaller, delicate parts which change frequently, still there are a number of applications where we need one or the other of the solvents we have discussed earlier. Now, painting was the second big field of activities where a lot of solvents are used. One example, the painting of bigger series of tanks. This is coating of parts for pumps. The most common ways of applying paint are either by spraying with compressed air with a pressure between 1.3 to 3 bars. Can be airless painting, where the paint itself is pressurized and sprayed through a nozzle, and can be electrostatically assisted painting, where an electrostatic field helps to attract the paint particles to the surface of the part which we want to coat. This applies to solvent-based paints as well as to water-based paints, because most of the paints actually today which are used in industrial coating are available as water-based paints. Problem with water-based paints is just the drying. We need slightly higher temperatures in drying, so we need a little bit more energy for drying water-based paints as compared to solvent-based ones. Now let's compare application. Compressed air application is simple, straightforward. Paint is here. Compressed air comes out of a nozzle, and by this we generate a jet of small paint particles. The spray pattern is adjusted by adjusting the nozzle appropriately. Gives very nice surface finish. Problem is, here usually I adjust the viscosity of the paint by adding quite some solvent. This is the application method with the most solvent. Here, when I spray, I use more than 50, maybe 60% solvent to adjust the viscosity of the paint. Airless application now. The paint is forced out of a small hole by pressurizing the paint. This means I can use much less solvent. Electrostatically assisted painting means that I apply a charge, a field, between the gun where I distribute the paint and the part. And this electrostatic field helps the paint particles to travel to the surface which they shall coat. We will see in a minute what these different application procedures, what transfer efficiency they show. Conventional air spraying reaches a transfer efficiency of maybe 30 to 40%. That means 30 or 40% of the paint which I spray out of the spraying gun actually hits my parts. The rest becomes overspray, the rest becomes waste of paints, and the respective percentage of solvent also is lost to the atmosphere. So conventional air spraying has the lowest transfer efficiency. Airless spraying is slightly better with an efficiency of 40 to 50%. High volume, low pressure, where I reduce the pressure in the spray gun to 1.2, 1.3 bar and replace it by a high flow of air, has a transfer efficiency of about 70%. And electrostatically assisted painting then, applying an electric charge, can give a transfer efficiency of up to 90%. So wherever possible, whenever I'm coating bigger quantities in conventional spray painting, I definitely should consider electrostatic application, because this will reduce the quantity of paint which I'm using, and consequently the quantity of solvent I'm losing by half. So whenever my task is to process bigger quantities of parts, I should opt for electrostatically assisted painting. With small quantities, small series, it's a problem, because the payback of the additional investment is not there. But most of the actually industrial application nowadays use electrostatically assisted application. New guns are available, spraying guns, which have a very laminar flow pattern. These are the areas with high velocity, and you see these are the new guns. They have very comparatively even distribution, very targeted flow of paint particles. These new laminar guns show a significantly reduced paint consumption, or much better transfer efficiency, because you can target the flow of the paint much better. In this example of covering these veins, the paint consumption was reduced from 200 milliliters per part to a little bit more than 100. So a careful choice of application technology, the right spray guns, the right pressure, and electrostatically assisted painting can reduce paint consumption and consequently solvent consumption by more than half. Now, two remarks regarding solvents. Nowadays, for most applications, water-based paints are available. And believe it or not, Mercedes, on all of their original paintings, are using water-based paints. And amongst their repair workshops, with this ad and others, they are promoting the use of water-based repair paints also, because it's a Mercedes policy, and it's a policy of most of the car makers nowadays, to go for solvent-free or almost solvent-free water-based painting. Because technically it's possible, it's accepted technology. The only drawback, as I mentioned earlier, in this respect is you need slightly higher temperatures for curing the paint. So solvent-based paints you can cure at lower temperatures, 60 degrees, 50 degrees, and for water-based paints you need slightly higher temperatures and slightly longer times for the water to evaporate and for the paint to solidify. For serial parts like sheet metal, like profiles, powder painting has become the standard application. So no solvent painting or spray painting, but powder painting, where powder is applied electrostatically to the parts. The powder is a resin, which is then cured at temperatures between 160 to 240 degrees and becomes a solid paint film, which is very strong, very endurable. These for profiles, for sheet metals, for frames and so on has become the standard technology. And this is solvent-free then. So no solvents in this operation in powder painting. Yeah, when we talk about painting, we always talk about moving a lot of air, because especially in spray painting, especially when painting with solvents, we need good ventilation. Ventilation, basically we have three approaches. First one is spray areas. That means a designated part of premises which is not specifically secluded, which is used for painting. This is actually not best practice, and it's sort of difficult to handle because we need good airflow here to allow collection of all the volatile organic carbons. Better is the use of spray booths, which means cabins which are completely secluded, which are made from fireproof material, which are much easier with respect to air handling, because you will have a controlled supply of air, extraction of air, filter mats, and then some treatment of the exhaust air, so that you have a very clearly designed and defined flow of air, which supports the painting process and which takes down the overspray into the filter mats. And spray rooms, which are then completely closed, which have a mechanical exhaust with a specific supply of air, which have appropriate heating and appropriate control of airflow, because there is a difference in air requirements, whether we are actually applying paint or whether we are just curing paint, is optimum, is of course a little bit more expensive. Here we see really professional painting application. The operator is fully covered, so whatever happens here with the paint, it cannot penetrate the skin. He is wearing a mask with filter cartridges, so the solvent cannot affect his respiratory system. Wearing goggles, so the eyes are safe, proper gloves. This is a professional working equipment, safeguarding the operator, and the spraying room is equipped in a way that also in terms of hazards for the environment there is none, because there is proper ventilation, there is proper electrical installations, there is proper grounding, there is proper lights which cannot draw any sparks and so on. Yeah, the formal requirement with us is that such a spray room must provide 30 air exchanges per hour. So every 2 minutes the air during application of paint must be exchanged. There are many small good housekeeping measures associated with a paint shop. Most of them basically mean good cleaning, meaning collecting or avoiding any build-up of residues of paint, of overspray, any pools or puddles of solvent, to minimize the risk for fire. By cleaning, by removing dust, by removing any residues, by removing contamination from conveyors and so on, the risk for fire, for an accident, is minimized. For the waste, there should be proper containers from metal with a lid, so that no solvent which might be in rags or in paint residues, no solvent can escape. Proper ventilation means fans which are non-sparking, so that there is no risk that in case of higher concentrations of VOCs there can be a fire. This actually, to my experience, is a considerable risk, that because of deposits in the air ducts and because of sparks, mostly from fans, at some point there is a problem with the fire. And this is actually, if you look into the statistics of accidents, this is one of the most frequent accidents with volatile organic carbons. We can avoid this to a big extent by monitoring the fans and by minimizing the build-up of residues in the air ducts by cleaning them regularly. Yeah, grounding is an important thing, especially when we are talking about electrostatic application of paint. The grounding between the part, the hook on which the part is put on the conveyor, and the conveyor chain is really important, so that the electrostatic field can develop. If there is a build-up of paint, being it powder or spray paint, which insulates the hook against the conveyor or the parts against the hooks, then the electrostatic field cannot work, and transfer efficiency will be lower. Surfaces, of course, should be regularly cleaned, as we discussed with the air ducts, to minimize pockets of paints, residues, and so on, which might at some point catch fire. Lights, if we use them in the booth, they need to be, if they are regular lights, they need to be separated from the booth by non-combustible panels. Why? To minimize the probability of starting a fire. A really important observation is that portable lamps, portable heaters, all these supporting equipment should not be used until it's checked thoroughly whether it can be used in this environment, because it might cause a fire. Spray gun cleaning. To summarize, it's not appropriate to use solvent during cleaning just by spraying it through the spray gun. Like this, we atomize the solvent and waste a lot of solvent. If possible, for cleaning the guns, the nozzles, the needles, we should use small gun washers with the closed cyclists. They look like little dishwashers where the solvent is recycled, is moved through the nozzles. They usually pay back in a year or 1.5 years. Yeah, just a remark. When talking about paints, we need to mention a few chemicals apart from VOCs, which are very dangerous to the operators and which need to be handled properly. The hardener of two-component paints contains isocyanides. Isocyanides irritate skin, eyes. They should be handled properly. In some old formulations of paints, lead was included as a corrosion protection. Lead we should not use because of toxic properties. And chromium in some pigments, chromium 6 also should be avoided wherever possible. There are a few heavy-duty coating materials where we probably cannot eliminate chromium, but in most of regular applications, chromium is not needed. The last 3-4 slides deal now with printing, because printing also is consuming still lots of organic solvents. This is just classical roll-on printing machine, 3 colors, offset printing machine with 4 segments. The system is these ink rollers are preparing the ink. This is the cylinder with the plate, with the cliché for printing. There are water rollers here, which are coating the areas which shall not show in ink on the paper then. And then by transfer we print the image which we want on the paper. In this water, actually, in this tamponing water, we have IPA, we have isopropylic alcohol, which is actually the major VOC used in printing. And then in cleaning, especially the ink rollers, we also usually use solvents. What can one do now to minimize the emission of organic solvents out of printing? Let's start with cleaning. Over the last years, and this is showing a comparison of cleaning solvents sold to the German printing industry in these periods. By 1995, still the vapor pressure of the solvents used for cleaning was quite high, actually. the flash point of most of the cleaning solvents was 55 degrees and lower than 20 degrees. This has shifted significantly. In 2006, it was already 2/3 of solvents which were used with a flash point between 50 and 100 degrees. So much less volatile organic compounds, much less emissions from evaporation during cleaning. So there is a trend to substitute highly volatile materials by less volatile ones. And in the last years, cleaning solvents on vegetable oil basis have established themselves in the market, and in many applications they are used now. These are basically derivatives of rapeseed oil, which work very nicely when wiping the ink cylinders to clean the ink cylinders. So there has been a significant shift over the last years between the types of solvents used, and nowadays many products are available with a low volatility. This is just an example, no need to dig into details here. Even low VOC options are available from many established suppliers of cleaning agents. We just need to ask them. We need to invite them to demonstrate their products. We need to ask for these products, because the natural habit is, of course, to sell the old stuff and not to experiment in fine-tuning the right chemicals for a specific application. So products are available, we just need to ask. I'm not showing you this video now because the most important things we see here for modern high productive offset printing machines, automatic cleaning machines on a water-based basis are available. This works very nicely. It's a little bit difficult to retrofit to old machines, but new machines we can specify and they work effectively. We talked about damping agents. We talked about the water there, where isopropylic alcohol is added, usually in a concentration of 3 to 10%. It is a little bit tricky. IPA-free fountain solutions are available, but they require usually some adjustments on the machine, some experience of the operators. So this is something for the future, to do without solvents in offset printing. But what we can do immediately is to control the concentrations to the minimum possible. And this means to provide the right measuring equipment so that the right concentration of isopropylic alcohol in the damping water can be adjusted, so that if we know we can do with 3%, we don't overdo and maybe use 4, 5, 6%, but 3%. And this requires some instruments so that operators can check the concentration. Because over a hot day in summer, some isopropylic alcohol will evaporate, the concentrations will drift, and the operators from experience will add. It's much more accurate and helps to save on isopropylic alcohol if the operators have a small measurement device to measure the actual concentration, and a small table which tells them how much to add in case the measured concentration is 2, 3, 4%. And the last suggestion is, especially in warmer climates during summer, from the tamping fountain we have evaporation. These evaporation losses can be reduced by cooling the tamping fountain. This guarantees not only less losses from evaporation, but this also helps for a stable quality and for stable conditions during printing, so the quality of the printing will be improved by cooling the ink fountain. Again, to summarize, all this is within the context of a circular economy. So ideally, we minimize on the extraction of natural resources and on the disposal, landfilling of waste by trying to close cycles wherever possible, by keeping materials in a confined circle, by using as little as possible. And I think for spray painting, for cleaning, for printing, we have explored quite a few options. And I dare say it's not unreasonable to say that solvent use can be reduced by 50% in many industries at present. We have this experience from Austria, and I'm quite confident that the experience from Belarusia will not contradict our experience. Yeah, I was using the cover picture of this brochure, which is for dairies, but a corresponding guide, a pocket guide, will be available for chemicals with a specific focus on VOCs. It's being translated at present, and it will be available for your use, per use distribution soon. So thank you. And questions are invited, of course.
Yeah. First question came from Armenia. What is the efficiency of modified alcohols compared to perchloroethylene? Какая эффективность? Вам переведу.
Efficiency in this case is difficult to answer, because in both regimes, actually with an optimized system, there was no waste and hardly any loss. So this is really a substitution of a material like perchloroethylene, which requires specific attention, to a material which is not considered problematic. There is some benefit, because during annual maintenance of the redistillation equipment, there will be some waste, which in the case of the use of perchloroethylene is hazardous waste, and which in the case of the use of alcohols was really minimum. It would be good maybe to discuss these practical experiences with the guys running this plant in Graz. They will simply tell you it's more practical not to use perchloroethylene, and there is less contamination